All right, we're going to work on part 2 of our lesson, which is acceleration. Now, acceleration is related to velocity. In fact, in calculus, we define acceleration as the rate of change of velocity with respect to time. So if velocity is changing, as in you're going from one speed to a different speed, then there's going to be some level of acceleration. If there is no change in velocity, as in, let's say we're going, let's say 20 kilometers per hour to 20 kilometers per hour, and we continue that over some interval, then we would say that there is zero acceleration. Okay, so no acceleration in this case. Okay, but if there is a change, so we go from 20 kilometers to, let's say, 40 kilometers per hour, excuse me, then we're going to say that there is some level of acceleration. Okay. All right. So, just like yesterday, we had a position function. Today, we have a velocity function. Okay. So, if we have an average acceleration versus instantaneous acceleration, it's the same idea. When we're looking at average acceleration, we're looking at how is some velocity function. So let me just draw something like this. Okay, so we can see that the velocity is changing, okay, at a increasing rate. It's not staying the same, right? So if we have a velocity time graph right here, we would have some point here, which we can call t1, and some point here, which we can call t2. And in that case, we would say that the average acceleration is a linear line between those 2 points. Okay? It's the slope between those 2 points. Whereas if we're looking at instantaneous, right, we have a slightly different definition in that we have some function, like so, and we're looking for what is the velocity at that particular time. Okay, and maybe I'll just call that t. Okay, and still it's the same graph. Okay, we're still looking at a velocity function. And so it just depends what we're looking for. Are we looking for average? Or are we looking at a particular speed at a particular time? We would call that instantaneous. Okay, and so like we said yesterday, if we have the velocity function, all we need to do is take the derivative to find the instantaneous. Very similar when we said when we wanted the instantaneous velocity, we just took the derivative of the position function, s of t. So if we're given s of t, okay, we said yesterday that we can find the velocity function by taking its derivative. Today, we're saying that if we take the velocity function and we take its derivative, that gives us acceleration function, right? So really, all we're saying is that acceleration is the second derivative of the position function. Okay? So if we take the derivative of the velocity function, that gives us acceleration. And we know that velocity is just the first derivative of the position function. So these are all related together. These are a big relation. Okay? So let's try a problem. So the position of an object in centimeters after t seconds is given by the function s of t. It says find the average acceleration from 0 to 5. So if we're looking for average acceleration, right, average acceleration would be the slope of a secant line. Okay. The slope of our secant line is going to be defined as v of t1, actually I think we said v of t2 in our formula, so v of t2 minus v of t1 all over t1, sorry, t2 minus t1. Okay, so that's our formula. Now, how do we get velocity when we're given position? Well, we need to take its derivative. So I'm going to go ahead and take the derivative of s of t, right? So s prime of t is equal to velocity. Okay, so in this case, my derivative becomes 3t squared minus 16t plus 0. I'm just going to leave the 0 out just to make our lives a little bit easier. And then what we're going to do here is we're just going to plug in our t values. So we have two t values. We have t1 right here, and we have t2 right here. Okay, so we're going to use those two values in our formula. And so I'm just going to plug those in. So we would have v of 5 minus v of 0 divided by 5 minus 0. All right, and so all we have to do is plug those into our functions up here. And so we would have 5 squared, which is 25 times 3, which is 75, minus 16 times 3, which is 48. So that's going to give us a grand total of, maybe I should write it up here. V of 5 gives us negative 5. Okay, and then V of 0, right, if we plug in 0, it's going to give us 0. All right, so we're going to have negative 5 minus 0 all over 5 minus 0, which gives us negative 5 over 5, which gives us negative 1. So what does that mean, the negative 1? The negative 1 tells us that the average acceleration is negative 1 meters per second squared. So what does that mean? That means that this object is actually slowing down. Okay? Or we could say it's accelerating towards the left, if you prefer to say that. So depending on how we started, we could say it's accelerating towards the left or it's slowing down. It's decelerating, if you prefer. All right. And then it says find the instantaneous acceleration at 3.5 seconds. Well, that's going to be the derivative. Right? So we need the acceleration. And the acceleration, we said, is equal to the derivative of v of t. Okay? So we're going to take that right here. And our derivative of v of t would be 6t minus 16. 6t minus 16. Okay? And then all I have to do is I have to plug in 3.5. So acceleration at 3.5 seconds is equal to the derivative at 3.5, which is equal to 6 times 3.5 minus 16. And then that gives us a grand total of 5 centimeters per second squared. And so that's the units for acceleration. Time is always going to be squared in that case. Okay. So whether it's minutes or seconds or hours, you're just going to square that number at the bottom because we're taking it in respect to time twice. Okay. What does this mean? This means that this object is changing its velocity and it's getting faster towards the right. Okay. All right. We have one more example, and this is a pretty comprehensive problem. It says the position of an object in meters after t seconds is given by this position function. Okay? And it happens to be the same as the last one, so that's great for us. Yeah, so we're going to analyze the motion of the object at t1. So when it says analyze, it wants us to say as much information as we can. So what is the object's position, its velocity, and acceleration, obviously. Right? So tell us as much information as you can about these three functions. So I've already given the position function, so that's pretty simple, right? So we're just going to look at s of 1. So s of 1 just means I'm going to take my function, I'm going to plug in 1 into the position function that I was given, and do some quick maths. Right? So 1 cubed is 1, minus 6 times 1, which is negative 6, that's negative 5, minus 15, so that gives us negative 21. Okay, and then we have to think about our units. So that's negative 20. I forgot to add 1. So we have negative 20 meters, right? That's our position. Okay. So this is sitting on the left-hand side somewhere. Okay. Then we have to talk about velocity. So velocity, okay, is the derivative of the position function. So the derivative of the position function is 3t squared minus 12t minus 15. Okay, so v of 1 is equal to s of 1, or sorry, s prime of 1. And so we have our derivative here. We're just going to plug it in to figure out what our velocity is at 1 second. Okay. So we calculate that, and so we have 3 times 1 minus 12 gives us negative 9, minus 15 gives us negative 24. And again, I'll be looking for units. So this will be meters per second, because we took the derivative in respect to time. Right? So our change is going to be in respect to time. So we're going to have seconds at the bottom right there. And so that means that we're moving towards the left at that speed. Okay. Then we have to look at acceleration. I feel like I need some color in here. Let's add some color. Let's do a of t. Okay, a of t, we said, was the derivative of the velocity function, right? So we're just going to go ahead and take the derivative of our velocity function, aka the second derivative of our position function. So we just take that derivative, so we're going to have 6t minus 12. Okay, and that becomes our derivative. And what's really nice about this is that a of 1 is just going to be 6 times 1 minus 12. So that's 6 minus 12, which gives us negative 6. And that's going to be meters per second squared, okay, in terms of our units. So what does that mean? That means that we're actually accelerating towards the left. Not only did we start on the left and we're traveling at negative 24 meters per second at 1, but we're actually getting faster. We're accelerating. Okay. So just write a little description, because it did say analyze. So at t equals 1, okay, or you could say at 1 second, the object is 20 meters left of the origin, traveling at 24 meters per second to the left while accelerating 6 meters per second squared to the left. So you don't have to incorporate too much physics knowledge in this, you just have to understand what the negative sign means. So we started 20 meters left of the origin, and we're traveling at 24 meters per second to the left, while accelerating towards the left. And that's the basics. All right, here are some practice problems for you to try. Okay. Thank you.